Here is a combined summary of the 2 pages. The ability to process time series data is crucial for various applications, from smart sensors to personal assistants and medical devices. Recurrent neural networks, RNNs, are well suited for such tasks, but their software implementation is computationally expensive. This work proposes a novel approach to implement RNNs in hardware using spintronic oscillators as dynamical neurons. Spintronic oscillators exhibit nonlinear high-speed dynamics, making them promising building blocks for neural networks. The authors simulate a multi-layer network of spintronic oscillators and demonstrate its ability to perform time series classification using standard machine learning tools. The network architecture consists of successive layers of dynamical neurons, connected by interlayer and intralayer connections. The neurons are represented by the autooscillator model, which describes the dynamics of the dimensionless normalized amplitude x. The model is simplified to dx, dt equals gamma x plus I, t, x, 1x, where gamma is the damping term, and I, t, is the time-dependent drive. The network is trained using backpropagation through time, BPTT, and PyTorch, achieving 89.83 plus or minus 2.91% accuracy on the sequential digits dataset, comparable to the equivalent software network. The authors also demonstrate that the spintronic network can be trained on input timescales over a 5-fold range, centered around a value depending on device parameters. Guidelines are derived to find these device parameters, including the neuron relaxation time, which must be larger than the input timescale, and the cumulative drive, which must be around 1. The network architecture is depicted in Figure 1, showing the connections between neurons and the high-pass filter and amplification factor used to keep the drives centered around 0. The dynamics of the power output of each neuron is given by dx, dt equals gamma x plus I, t, x, 1x, with the drive I, t, depending on the outputs of the previous layer and the trainable biases. The authors apply a fixed bias on top of the trainable biases to each neuron to keep their output above 0 and below 1. The spintronic network is evaluated on a time series classification task, specifically the sequential digits dataset, consisting of 1797 grayscale 8 by 8 pixel images of handwritten digits. The network is simulated using PyTorch and the differential equation, 2, with the input presented pixel by pixel as a time series of 64 input points each. The network's internal state is reset after processing each image, and the trainable parameters are updated using backpropagation through time, BPTT, and batches of 120 images. The connectivity density is set to 0.5 for both interlayer and intralayer connections. The network achieves an accuracy of 89.83 plus or minus 2.91%, comparable to a standard continuous time recurrent neural network, CTRNN, with the same architecture. The spintronic network's performance is attributed to its natural implementation of a CTRNN, with the main difference being the intrinsic bounding of the internal state of the spintronic neurons. The network's adaptation to different timescales is studied by training it on series with varying input timescales. The accuracy depends on the time interval between input points, with a maximum accuracy maintained over a wide window of timescales. The network's performance degrades significantly when the timescale is well below or above the optimized point. The dynamics of the spintronic neuron rely on a competition between the current drive and the damping. The relaxation time of the neurons must be larger than the time between 2 input points, and the cumulative drive divided by the relaxation time must be roughly equal to the damping. The learning rate must also match the input timescale, with faster inputs requiring higher learning rates. The network's performance is visualized in Figure 2, showing the accuracy versus the time interval between input points, as well as the evolution of a neuron from the third layer for different inputs. The results demonstrate the importance of designing networks adapted to learn tasks with specific timescales. The guidelines for designing such networks are derived from the study of the spintronic network's behavior at different input timescales. The research paper presents a multi-layer neural network where neurons are spintronic oscillators, leveraging transient dynamics for memory and nonlinearity. The network is trained with backpropagation through time, BPTT, and standard machine learning tools, achieving 89.83% accuracy on a time series classification task, comparable to a standard recurrent neural network. The paper explores the impact of time-scale adaptation on the network's performance. Figure 3 shows the accuracy versus the time between two input points, increment t, for different neuron relaxation times, tau, and learning rates. The results indicate that the best accuracies are obtained when the cumulative drive is around 1, provided that the input timescale is larger than the relaxation time. The authors recommend setting the learning rate in the range of 1/100th of the optimal weights values. The paper also investigates the effect of connection density on the network's performance. Figure 4 shows the accuracy versus the density of connections, demonstrating that the intralayer connectivity can be reduced to 10% without losing accuracy, while the interlayer connectivity can be reduced to 20%. The global connectivity is optimal around 50%. The authors propose using spintronic resonators as physical implementations of the synaptic layer, which can respond fast enough to preserve the neuron dynamics. They estimate that the network would consume about 40 pJ per image, making it a promising approach for time series processing at low energy cost. The paper concludes by highlighting the potential of spintronic oscillators for time series processing and providing guidelines for designing and training such networks. The results demonstrate the feasibility of scaling up spintronic neural networks for complex tasks while reducing energy consumption. The authors also acknowledge the limitations of their work, including the need for online training leveraging the physics of the network, which is out of the scope of this paper. Here is a combined summary of the 2 pages. Recent advancements in neuromorphic computing have led to the development of novel architectures and algorithms inspired by the human brain. Researchers have explored various platforms, including photonic recurrent neural networks, mechanical oscillators, and spintronic devices, to implement analog recurrent neural networks. For instance, the BrainScale's 2-accelerated neuromorphic system with hybrid plasticity has been demonstrated, showcasing the potential of neuromorphic computing for complex tasks. Studies have also focused on the use of spin-torque nanooscillators for reservoir computing, where the frequency, phase, and amplitude of the oscillators are utilized to process information. Physical reservoir computing based on spin-torque oscillators with forced synchronization has been explored, and granular vortex spin-torque nanooscillators have been proposed for reservoir computing. Furthermore, researchers have investigated the application of spintronic devices for neuromorphic computing, including the use of spin-Hall nanooscillator arrays for mutually synchronized operation. Multilayer spintronic neural networks with radio frequency connections have been demonstrated, and dynamical neural networks based on spin transfer nanooscillators have been proposed. Theoretical frameworks, such as nonlinear autooscillator theory, have been applied to understand the behavior of spin-polarized currents in microwave generation. Machine learning algorithms, including backpropagation and dynamic error propagation networks, have been employed to optimize the performance of neuromorphic computing systems. Optimization frameworks, such as Optuna and Atom, have been used to tune hyperparameters in neuromorphic computing systems. The approximation of dynamical systems by continuous time recurrent neural networks has been explored, and deep physical neural networks trained with backpropagation have been demonstrated. These studies highlight the rapid progress in neuromorphic computing and the potential of novel architectures and algorithms for complex tasks. However, limitations and assumptions, such as the need for further optimization and the reliance on specific materials and devices, are acknowledged, and future work is proposed to address these challenges.